Hello students, I am Professor Dheeraj Kumar Singh from Department of Mechanical Engineering, Sagar Group of Institutions, Sistekar, Bhopal. Dear students, today we are going to discuss Carnot Cycle and Carnot's Theorem. So let's start the class. What is Carnot Cycle? Carnot cycle is a reversible cycle and is an ideal hypothetical cycle in which all the process constituting the cycle are reversible. Means in Carnot cycle, whatever the processes we will be using, all processes will be reversible processes. Carnot cycle is a reversible cycle, yes. For a stationary system, as in a piston cylinder machine, the cycle consists of the following four successive processes. In given figure we can see this, right? So this is a piston cylinder arrangement, this is a cylinder, and this is our piston, and this is a dithermic wall, and this is a adiabatic cover. So dithermic cover is that kind of cover from which heat transfer can take place, but from adiabatic cover there will be no heat transfer. So in isothermal processes we will use this dithermic cover, and in adiabatic processes we will use this adiabatic cover B. So this dithermic cover is denoted as A and this adiabatic cover is denoted as B, right? And this outer portion of the cylinder, we can see this outer portion of the cylinder is also a adiabatic cover, right? So here we can see source T1 and in the bottom sink T2, right? And here we can see WE is the work done by the system adiabatically or reversibly, and WP is work done upon the system reversibly or adiabatically. So this is the basically a figure of Carnot heat engine and stationary system. So there are four processes in Carnot cycle. First is reversible isothermal process, that is also known as heat addition or expansion process. Second process is reversible adiabatic process, that is also known as adiabatic expansion. Third process is reversible isothermal process, also known as heat rejection or compression process. And the fourth process is known as a reversible adiabatic process, that is also known as adiabatic compression. So in the next slide we will be seeing the graph on PV plane of this particular Carnot cycle, then we will be able to understand the things. So here heat is being supplied in process 1 to 2. Heat is being supplied in process 1 to 2, right? So what will happen we will see in the next slide. And here we can see that heat is rejected. Q2 is our heat is rejected from the system to the sink or the surrounding. So this is basically this C point, a reversible isothermal process, means heat rejection process. So the Carnot cycle consists of two isothermal processes and two adiabatic processes. So moving to the next slide, we will understand each and everything very clearly. So in process 1 to 2, here we can see this is our PV plane, right? And this is the diagram of Carnot cycle. So process 1 to 2 is reversible isothermal process or heat addition process. We can see here Q1 is the heat supplied in process 1 to 2, right? Then process 2 to 3 is our reversible adiabatic process, right? From in that particular reversible adiabatic process, work is done by the system. WE is our work is done by the system. Then we will move to process 3 to 4. This process 3 to 4 is reversible isothermal process. So this is reversible isothermal process in which heat is being rejected, that Q2 heat is being rejected to the surrounding. And the last process is 4 to 1. This is also known as reversible adiabatic process and adiabatic compression process, in which we can see work is done upon the system or work is done on the system. So that is denoted by WP. In the previous slide we can see here WE and WP. These are the two processes of isothermal system, and heat supplied and heat rejected are the processes of this heat supplied and heat rejected are the processes of isothermal system, and this WE and WP are the two particular work transfers of the adiabatic system. So here you can see in process 1 to 2 heat is supplied right? And this is a reversible isothermal process. So a reversible isothermal process in which heat Q1 enters the system at T1. This temperature is T1. If we will draw the isothermal curve on Ts plane, then we can see that 1 to 2 process 1 to 2 will be a straight line, that is on temperature line. So enters the system at T1, heat Q1 enters the system at T1 reversibly from a constant temperature source at T1 when the cylinder cover is in contact with the dithermic cover A. Right, that means heat transfer is taking place. So in that case, the internal energy of the system increases. Yes, obviously if we will supply the heat to a system, then obviously its internal energy will increase. So from the first law of thermodynamics, we know del Q equal to du plus del W. So we can write that heat supplied is Q1 and change in internal energy is final internal energy minus initial internal energy plus work done. So here we can see that in isothermal process, for an ideal gas, internal energy is a function of temperature. So internal energy at inlet is equal to internal energy at outlet. So U1 will become equal to U2. So the equation will become Q1 equal to W12. So that will be our equation 1. Similarly, in process 2 to 3, we can see this is a reversible adiabatic process. So reversible adiabatic process in which the dithermic cover A is replaced by the adiabatic cover. That means heat transfer will take place here. That means Q is 0. Here no heat supply we can see, right? So the system adiabatically and reversibly at the expense of its internal energy. I am repeating it again. A reversible adiabatic process in which the dithermic cover A is replaced by the adiabatic cover B and work WE is done by the system adiabatically. If we are getting work done by the system, then that work will be positive, and reversibly at the expense of its internal energy, and the temperature of the system decreases from T1 to T2. So now by using first law of thermodynamics, heat transfer is 0, so Q equal to 0. So final internal energy minus initial internal energy plus work transfer W23. This will be our equation number 2. Then we will move to process 3 to 4 in which heat is rejected. Q2 heat is rejected. So what will happen? Let's see. A reversible isothermal process in which B is replaced by A, right? So B is replaced by A. That means now this B is our dithermic wall, right? So this is not an adiabatic process now, right? And heat Q2 leaves the system at T2 to a constant temperature sink at T2 reversibly, and the internal energy of the system further decreases. Obviously, if heat will reject from the system, then the internal energy of the system will decrease. So from first law of thermodynamics, we can see heat is rejected, so we will take negative sign, minus Q2 equal to final internal energy minus initial internal energy, that we are applying first law of thermodynamics, minus W34. So why we are using minus W34? Because here we can understand, yes, in this figure you can see here we are expanding. Here heat addition process takes place, here expansion process takes place, but this is compression, right? Heat rejection is taking place and here is this compression. So work is done on the system here, right? So work is done on the system. If that kind of thing we will see, then we will understand that our work transfer will be negative, right? So minus Q2 equal to U4 minus U3 minus W34, and for an ideal gas we know internal energy is a function of temperature, so U3 equal to U4, so minus Q2 equal to minus W34. That will be our equation number 3. Now move to the fourth process. Fourth process is our reversible adiabatic compression process 4 to 1, right? So a reversible adiabatic process in which B again replaces A and work WP is done upon the system reversibly and adiabatically, and the internal energy of the system increases and the temperature rises from T2 to T1. Yes, obviously when work is done upon the system, when you will do some work on the system, then also reversibly and adiabatically, then its internal energy will also increase and the temperature rise will take place from T2 to T1. Then after applying first law of thermodynamics, we know this is adiabatic process, so heat transfer will be 0. So U1 minus U4, initial internal energy minus final internal energy, minus W41, because work is done upon the system. So we will take work as negative. So adiabatic cover, that means heat transfer 0, and dithermic cover, that means heat transfer will take place. So now we can see we are having 4 equations: equation number 1, equation number 2, equation number 3 and equation number 4. Then when we will add these 4 equations, right, then we will get that it is a cyclic heat engine. So a cycle is said to be a reversible cycle only when each process in a cycle is reversible. If each process of the cycle is reversible, then the cycle completely can be called as reversible cycle. So 2 reversible isotherms and 2 reversible adiabatics, that means 2 reversible isothermal processes and 2 reversible adiabatic processes constitute a Carnot cycle, right, which we have seen represented in PV plane earlier, right. So here we can see, and these are 2 isothermal processes, right, and these are 2 adiabatic processes, we can see. So dear students, now we are summing up the equation 1, 2, 3 and 4. Then we have Q1 minus Q2, right. From equation 1 and equation 3 we will get Q1 minus Q2, and from equation 2 and 4 we have got W12 plus W23 minus W34 plus W41. So this is nothing but summation of Q net equal to summation of W net. So this is first law of thermodynamics for a cycle. So a cyclic heat engine operating on the Carnot cycle is called a Carnot heat engine. Okay. My dear students, a very important point I want to discuss here, that we are combining 2 isothermal processes with 2 adiabatic processes. So you can see here, to realize isothermal conditions, the process must be carried out in a very slow manner. That means isothermal process is a very slow process. And to realize adiabatic conditions, the process must be carried out in a very fast manner. Adiabatic process is a very fast process, and hence the 2 combinations are not possible in a cycle, right. And therefore Carnot cycle is a theoretical cycle, a ideal cycle, and this cycle is only used for comparing or comparison with other cycles, right. So this is not an actual cycle. Carnot cycle is not an actual cycle. Why? Because the combination of very slow processes and very fast processes is not possible. An isothermal process is very slow process and adiabatic process is very fast process. Now dear students, we will move to Carnot's theorem. What is Carnot's theorem? So actually Carnot stated that, it states that of all heat engines operating between a given constant temperature source and a given constant temperature sink, none has a higher efficiency than a reversible engine. That means Carnot told us that if we are having a given constant temperature source and constant temperature sink, then the efficiency of that particular reversible engine will be the highest one. None other engine has the higher efficiency than that reversible engine. So we will see that how can it will be possible, what are the statements of Carnot. So let us see what he has told us and how we are going to prove it. Let 2 heat engines EA and EB operate between the given source at temperature T1 and given sink at temperature T2. So here it is source T1 and here it is sink T2, and we are having 2 engines, that is one heat engine A and one heat engine B. Heat supplied to heat engine A Q1A and heat supplied to heat engine B is Q1B, right, and heat rejected is Q2A from engine A, heat engine A, and heat rejected Q2B from heat engine B. And net work from heat engine A is WA and net work from heat engine B is WB. So 2 cyclic heat engines EA and BB operating between the same source and sink, of which EB is reversible. So here we have taken EB as reversible cycle, right. EB is a reversible. We have decided that the heat engine, our B heat engine, is a reversible heat engine. means that we can change the direction of that heat engine. Other things will remain constant, but the direction of the engine can be changed, heat engine can be changed. But this one is not reversible, this one is a normal, it may be irreversible, but this B is reversible. So here we can see, dear students, let EA be any heat engine and EB be any reversible heat engine. Clearly here it is saying that EA be any heat engine and EB is reversible heat engine. So we have to prove that the efficiency of EB is more than that of EA. According to Carnot's theorem, the reversible heat engine efficiency will be greater than the efficiency of other heat engine. If that heat engine is not reversible, then the efficiency of reversible heat engine will be more. So let us assume that this is not true, and efficiency of A is greater than efficiency of B. So what we are doing, we are assuming a wrong thing, that let us assume EA is efficiency of A is greater than efficiency of B, which is not correct, but we are assuming, right, we are assuming it. So let the rates of working of engines be such that Q1A equal to Q1B equal to Q1, means heat supplied to heat engine A and heat supplied to heat engine B will be same. So if we have assumed efficiency of A is greater than efficiency of B, then the formula of efficiency is net work divided by heat supplied. So WA divided by Q1A is greater than WB divided by Q1B. So Q1A and Q1B will get cancelled out because they are same. So what we are getting here, WA is greater than WB, means net work in A we are getting more than the net work in B. Right. So we have assumed, we have taken a wrong assumption, and according to that wrong assumption our network at A is greater than network at B. So let us move how we can justify the Carnot's theorem that Carnot was right. Right now we are saying that we have taken the opposite statement of the Carnot. If our opposite statement of the Carnot will get wrong, then yes, Carnot was right. So we are doing this here. So in the next slide we can see, now let EB be reversed. So we have reversed that our heat engine B, right, because it is a reversible heat engine. So let EB be reversed. Since EB is a reversible heat engine, the magnitude of heat and work transfer quantities will remain the same, but their directions will be reversed. Yes, the heat transfer or the work transfer will remain same, but the direction is reversed. As shown in the figure, we can see, as we have discussed earlier, that WA is greater than WB according to our assumption. So some part of WA equal to WB may be fed to drive the reversed heat engine EB. That means what we have seen, we have taken the efficiency of A greater than efficiency of B, and the result of that WA is greater than WB. So what we can do, we can take WB amount from WA and we will try to feed our reversed heat engine B, right. So it is written here, some part of WA equal to WB may be fed to drive the reversed heat engine EB. So what will happen, since Q1A equal to Q1B equal to Q1, so the heat discharged by EB may be supplied to EA. So it is saying here, if Q1A is equal to Q1B, so this particular Q1B heat discharged can be directly supplied to this EA. So we will not have the need of this source T1, right. So the source may therefore be eliminated. So the net result is that EA and EB together constitute a heat engine. So EA and EB will together constitute a heat engines. That means we are producing the net power here, net work here, WA minus WB, by exchanging heat with a single reservoir. We do not have the need of that source. That is violating our Kelvin Planck statement, and what we have assumed earlier, that the efficiency of A will be greater than the efficiency of reversible engine B, that is wrong. So here in the last sentence you can see, a heat engine which operating in a cycle produces net work WA minus WB while exchanging heat with a single reservoir at T2. This violates the this violates the Kelvin-Planck statement of second law. Hence the assumption that efficiency of A is greater than efficiency of B is wrong. Therefore, efficiency of B will be always greater than the efficiency of A. Right? So finally, what Carnot had said to us, or what was the Carnot statement, that is justified here. That efficiency of a reversible heat engine is always greater than the efficiency of a irreversible heat engine. So important points with respect to reversible cycle we can discuss, like for different reversible engines working between same temperature limits, the efficiency is same. Efficiency of a reversible cycle is independent of working fluid, and the efficiency of a reversible cycle depends only on temperature limits. So that's all for today's class, dear students. Thank you.